Okay, so our first speaker is Martin Bojowald. Thank you very much, Martin, for having accepted our invitation. Martin will contribute with a talk entitled The Cycles of Bouncing Cosmology. Thank you very much, Martin. I leave it to you.
Well, thank you for the invitation. Yeah, I'll be talking about bouncing cosmology, mainly, which I understand as something like this here. So the Big Bang in these models is preceded by a collapsing universe. And in many cases, people try to glue these together to cyclic models. So there would be many cycles of collapse and expansion. But as I'll try to explain, it's pretty hard to get even a single bounce. So what I refer to as cycles is more in the theoretical developments, which are going back and forth between bounces that seem to be possible and no-go theorems that rule out some of them. A little bit of history here. So it started almost 100 years ago, soon after Friedman, Lemaitre, and then Robertson Walker derived the first expanding solutions. And I think it was 5 or 6 years later when Richard Tolman started thinking about what might happen if the Big Bang did not start with a singularity, but with the collapse of a preceding universe. And he discussed questions like what happened with entropy. If there's a really long history of the universe, and entropy would build up, and that would suggest we should have really large entropy right now, which might be a problem. I won't talk much about these issues, but that's something that he discussed early on. And then the next few decades were when the Big Bang model was really developed with all the matter ingredients, the primordial matter, nucleus synthesis, and the cosmic microwave background. And then finally observed by Penzias and Wilson. So this was when people didn't think so much about bounces, but really just trying to understand the early Big Bang phase in our expanding branch. But it didn't take long for other people to think about bounces with more precise mechanisms than Tolman. After that, more details in the measurements, COBE, and then WMAP first data release was 2003, and then there were many more precise results. But even during this time, then bounce people were still active and thought about what the bounce could mean about maybe some small deviations compared with standard Big Bang models. And then since about 2000, there were various ideas about how to derive bounces from quantum gravity, so theories of space-time structure, from loop quantum gravity and string theory. And I'll talk about some of these. Now, if we look at the dates more precisely, we can see that there's a relationship between other cycles in economical developments. The 30s were the Great Depression. So everything in blue here refers to bounce ideas. And if you compare booms with collapses of economy, there's a relationship. So the post-war boom was the main developments of the Big Bang model. The oil crisis basically ended that. And then the recent observations start with the dot-com bubble until that also crashed. Well, that doesn't mean there's a causal relationship between these events, but there might be at least a subconscious relationship, because I have to emphasize we don't have any observations about bounces. We have lots of observations now about the Big Bang model, so Earth would happen after the bounce, but there's no indication that there had to be a bounce or cyclic models. So everything is based on theory, and that means we have to use certain assumptions or expectations. It's all very vague initially, and so researchers, modern cosmologists, can easily be, at least subconsciously, influenced by surrounding events like these economical cycles. And of course, the recent interest still ongoing in bounce models is consistent with this relationship. So in everything I will tell you, keep in mind, there's no observational confirmation at this point. But we do have math, and so we can at least test bounce models. So I will actually focus more on what prevents bounces from happening than how bounces could be initiated by physical effects. So the main problem is that the Big Bang model in the standard description, general relativity, really starts with a singularity. So infinite density, infinite temperature, zero size of the universe. And the equations just break down. So we have to find an extension, first of the equations of the math. And then it's easy to assume that such an extension would also extend the history of the universe 2 times before the Big Bang. So this would be something like replacing the dashed line here, which just goes down to zero size, infinite density, by a bouncing solution like this. Now, all this in classical general relativity is described by 3 equations. If we just assume an isotropic universe, so just the overall size, we have Friedmann's equation for the expansion rate, the Hubble parameter, related to the energy density. Energy conservation tells us how the energy density should change in an expanding universe just by dilution. And different kinds of matter react differently to being diluted. So the pressure describes how thermodynamically matter reacts to this expansion. And then we usually have energy conditions. So the energy density cannot be arbitrarily small. They are usually positive. But turns out the pressure can also contribute. So if there's some positive pressure, the energy density could actually be somewhat negative. But all the matter theories that we know well obey at least this inequality here. So these 3 equations, we can take a time derivative of the first equation to get the acceleration rate from the expansion rate, and then replace the time derivative of rho on the right-hand side by this combination here. And if we go through the whole procedure, turns out the last inequality gives us a simple inequality for the acceleration rate, which means it cannot be negative. Sorry, it can be positive. So I have to hold the whole thing. That means we can have something like the dashed line here, which is expanding, but more and more slowly. So the expansion rate is decreasing. But anything that bounces like this would have an increasing expansion rate around the bounce points, in this case, between the 2 dotted lines. And that's ruled out by this procedure, and there are more general singularity theorems that tell us even if we go beyond isotropy or homogeneity and consider all kinds of matter theories, we always have a singularity in the past. Which means if we want a consistent bounce picture, we have to violate at least one of these 3 equations. We usually don't want to mess with energy conservation, so that leaves 2 of them. And the first models focused on the last equation, which maybe because it's the motivation isn't so strong. We know that energy should be kind of positive, but then it's energy in the very early universe where we don't really understand matter as a plasma or maybe quark-gluon plasma too well. And so maybe this can be violated. So that's was almost, I think, Tolman's motivation. And more specifically in follow-up models, the argument is we usually have a very sharp value of energy in classical physics, but if quantum mechanics comes in at high density, then we have uncertainty relations, and the energy and time have a form that's very similar to position and momentum. So in short time intervals, the energy can easily fluctuate. And if the fluctuation is large enough, it might take it, at least statistically, to negative values. So this positive energy isn't so strong in quantum physics as it seems in classical physics. And it's maybe encouraging that dark energy more recently also seems to require a violation of the conditions. So first of all, it's accelerating expansion. And then based on the Friedmann equation, again, that would require a violation of the energy condition. The only problem is we don't really understand dark energy any better than the Big Bang singularity, but it's at least two indications that tell us we might need positive acceleration. But if it's really based on fluctuations and the uncertainty principle, that means it's really just a statistical effect. And for that to happen in the whole universe, just at the right time to prevent the collapsing universe from reaching a singularity, it's hard to argue that that whole process is very likely. I put this in a parenthesis here because I wasn't planning to talk about this too much, but we also have to ask what it really means to have quantum fluctuations, which are always statistical in a single universe that we can observe. And one way to make sense of this is to say the universe is not exactly homogeneous. So we can split it up into a large number of approximately homogeneous patches. And this gives us a statistical ensemble on which we can define quantum fluctuations. So that at least makes sense of these statistical notions. But again, if we try to apply this to our collapsing predecessor universe, then that means that only some of these patches would really get negative energies from fluctuations. They would bounce, the others would still collapse in a singularity, and it would just break up the whole universe. So it's very hard. There are possibilities, but really a completely consistent picture is very hard. So more recently, then there was a second possibility. So instead of violating the last equation, energy positivity, we can try to violate the first equation, the Friedmann equation. And that's usually done in a quantum gravity. So the idea is that general relativity is just a low curvature, low energy description of the fundamental theory. And if that's the case, then we can expect the Friedmann equation to be modified at high density. Also here, a major challenge is that it must be consistent with symmetry principles like coordinate invariance, which we know is true in general relativity, generally covariant. But if we just start modifying the Friedmann equation, which just applies to isotropic models, it's not clear that there's an extension that could consistently describe any space-time, including inhomogeneity. And so there's also a big obstacle here. Some examples are higher curvature effective actions. So these are also guaranteed to be covariant. So in the action principle, we just replace the usual Ricci scalar with the function, or it could also be other curvature invariants. But it's not that easy to get generic bounces from these modifications. The other possibility is if there's really quantum space-time, then even the geometrical structure should be modified. Quantum space-time could be discrete, for instance, and then we don't have a continuum measure like what we're integrating in the standard action principle. So there might be some other non-Riemannian geometry which describes space-time at these high densities. But again, we need to obey consistency conditions. Geometries also are not arbitrary, or different properties have to be interlinked. And if that's possible, we can get something like this, really a discrete expanding universe. So it might, it's like these individual patches, and each of them would have no structure or be homogeneous. But then each of them can expand, or the number of them can increase, and both contribute to the expansion rate of the universe. And maybe they could also tell us something about the universe before the Big Bang. Now here, so we are trying to modify the Friedmann equation. And a simple version on which many models in loop quantum cosmology are based is of this form. We don't modify the right-hand side. And we use a sine function here instead of the standard Hubble parameter squared. There's a modified Hubble parameter h tilde. And because it has units of 1/time, we need a length parameter here that is a free parameter and comes from this underlying quantum gravity theory. The specific sign function, I'll explain this a little bit later on, also comes from a motivation in quantum gravity. So in this case, initially, we don't know what this h tilde is. It's not the standard expansion rate, but this whole combination defines the energy balance of our contributions to the universe. So we can use it in Hamilton's equations, just like the standard energy function, and really derive the relationship between h tilde and a. So we get a consistent set of equations within this model. And we don't even have to solve them. If we just look at this equation up here, if we use the modification on the left-hand side, L is a constant, c is still the speed of light is constant. So it's a bounded function on the left, which means that the energy density on the right must also be bounded. So the singularity is avoided in some way. And so that gave rise to a lot of hope initially about using this for a bouncing model, like this one here. So this would be a picture of a wave function evolving according to this equation. So collapse to some non-zero size here, not, well, a finite, but still very large density, and then expansion on the other side. A few parameters. So there's this initially undetermined parameter L, but in quantum gravity, we know that we have to, well, somehow combine gravity and quantum physics. So we can first start with the corresponding constants, which is Newton's constant G and then Planck's constant H bar. And turns out, as Planck already knew, there's a unique combination together with the speed of light that gives us a length parameter. It's called the Planck length. And so it's natural to expect that some quantum gravity phenomena start happening on the scale. We know all the values, so that's a very tiny number. And for cosmology, the corresponding density is also important. So that's what we would get as an upper bound here for the mass density if we just use the Planck length as this L parameter here. So if we work this out, the Planck density, it's more than 1 trillion solar masses in just a single proton-sized region. So it's extremely large, larger than anything we can probe directly in the lab. But it's not infinite. So it would be a non-singular description of the universe. Heuristic interpretation here. So to get a bounce, we need some kind of repulsive contribution from gravity. So we know in everything we've measured, gravity is always attractive. But maybe quantum effects can change that and give us a repulsive force. And one way to understand how this could happen from discrete space is illustrated here. So if we just sample a wave on some discrete space, the number line here in 1 dimension, then it can be pretty accurate if the wavelength is much longer than the discreteness scale. But if we get closer or even below the discreteness scale with the wavelength, we see that the sample points line up along a different wave with a much longer wavelength. So, and longer wavelength means less energy. So somehow just having a discrete space means that we have an additional repulsive effect that can push out energy or prevent energy densities from getting too large. And that's what we see in these simple bounce models. There's an underlying theory. I won't talk much about this, but the idea is to try and generalize what we know from standard matter theories. So everything initially is based on the harmonic oscillator. We have creation operators that can change the energy of the state, starting from the ground state. In quantum field theory, that's generalized to multiple particles and their interactions. And here instead of the ground state, we have the vacuum. In loop quantum gravity, people try to extend this even to space and time. So there are creation operators for spatial ingredients, which for mathematical reasons are one-dimensional loops. So if we have many of them, a highly excited state, we have something on the right-hand side here which might well approximate continuous space. But if we try to remove most of these loops to understand the underlying states, we get more discrete structures, so not close to a continuum anymore. And if we remove all of them, we still have a state like the ground state or the vacuum, but it's not like the standard vacuum, which doesn't have any particle excitations, but it still has space. If we remove all these loops in quantum gravity, then even space is removed. So it's emptier than empty space. I guess the emptiest space ever constructed mathematically, but we don't really know what it means. But mathematically, it is at least a consistent structure. And the sign function in the modified Friedmann equation comes from the form of these HL operators. So there's some underlying motivation for the modification. But also here, even though there are all these heuristic pictures, which makes things at least plausible, there are lots of questions if we start thinking more about it. So the claim is that discrete space might stop the collapse of this predecessor universe, and that's been confirmed in exactly homogeneous models. Now, the tricky part is going beyond homogeneity, or even within homogeneity, including all the quantum effects. So in most of the studies so far, not all of them have been included for sometimes implicit, sometimes explicit assumptions. And so the first question is, if we really have repulsive gravity, that just means we have an additional potential barrier that we would not have in classical gravity. But quantum physics doesn't really care much about potential barriers. It would just tunnel, the wave function would just tunnel through them. And so even though it might push back some states, others might still tunnel through and reach the singularity. So it's not so clear that all quantum states will be non-singular. The second question is a little bit related. So the first models, as I mentioned, use completely homogeneous space. So there was no structure in space. And that's well justified at late times. So recent cosmological observations, galaxy surveys showed that the matter distribution on very large scales is really much more homogeneous than we see on smaller scales. So at late times, that's a reasonable assumption. And if all of space can be treated as a single homogeneous quantum object, it's macroscopic. So we don't expect a lot of quantum features to happen that might give rise to tunneling. So normally we see them only for a microscopic. The problem is, while it's justified at late times for the whole universe, homogeneity is also in some way justified at early times. There's the Belinsky-Kolodnikov-Lifshitz scenario, which tells us that if we follow the collapse of the universe, then we can see numerical solutions, for instance, show this nowadays. We can see that structure forms very rapidly. For instance, different black holes get closer, so it can collapse, and all kinds of other structures can form. But if we are very close to a singularity in the classical analysis, then at least on very small scales, we can still assume homogeneity. That's still a good approximation to our solutions. But while it preserves homogeneity, it takes us from a macroscopic object, the whole space of an entire universe, to microscopic objects, just these tiny little homogeneous patches that remain in this picture. And for these tiny objects, again, we expect lots of quantum effects like tunneling and other effects. That might be a way then for bounces not to happen, or to happen only partially. And then finally, if we look at details of these singularity theorems that tell us how GR would always end in a singularity, these theorems have to be avoided in some way. So in isotropic models, we can avoid them by modifying the Friedmann equation. But if we go beyond homogeneity, it's harder to see how that happens. And it turns out the singularity theorems don't need a lot of assumptions about the specific dynamics. So they're very general. So even if we modify general relativity, they are still correct. So if we now have a bounce instead of a singularity in these modified Friedmann models, the question is, how can that really evade the singularity theorems and with their statements about space-time structure? What is the underlying space-time structure of these modified models and their bounces? Now it turns out, so that was the most recent analysis, it is indeed very tricky. So space-time can change drastically at high density. And it's not like what we normally know from space-time around us these days. So it's basically, I'll make sense of all these statements in the following slides, but as a summary, at the Big Bang, the space is basically too dense to let even time pass through. And so it turns out in a consistent extension to inhomogeneity with consistent space-time structure, we don't actually have space-time at high density. We just have four-dimensional space. And now the question is, we might be able to avoid infinite densities. That's what these, like the pictures I showed and bounce models showed. But the question now is there really a deterministic relationship between the predecessor universe and our expanding universe? Now to show this, I have to go into some of the technical ideas. So we have to analyze space-time structure. Space-time structure basically means we have to know the underlying symmetries, like rotations or boosts if it's space-time, and then see how they can still operate at high density when we start modifying the Friedmann equation. So the basic idea is initially very simple. So we all know what a rotation looks like. There's an angle as the main parameter to determine how it rotates. And we usually draw it in a spatial diagram. We can repeat the construction in space-time. In this case, the symmetry transformation is not a rotation, but a boost. And the angle is replaced by the speed of a new observer. And if we use the relativity principle, so the speed of light should be unchanged by these transformations, we can derive what these symmetry transformations mean. So that's shown here. It's a little more loaded diagram because there's more ingredients, but we can start the standard diagram for X and CT in black. And then since we don't really have any intuition about space-time geometry, we have to derive it. And first, to make sure we draw the correct time axis here, we can define this by an operational procedure as the set of all points in space-time that are defined by light rays starting at opposite sides from the origin and then moving inwards toward the origin. So the blue lines are light rays in this diagram, and they indeed meet on the time axis here. Now, if we apply a boost, then that means the x-axis is transformed in some way. And to derive the new position of the time axis, we repeat the procedure. We can still draw light rays because we know that the speed of light is unchanged. But now we start again from opposite sides from the origin. And because if we push the x-axis up on the right-hand side, the light rays here start later than they do on the left, so they have less time to move. They can move a shorter distance, and so they meet now a little bit to the right. So instead of using a standard right angle, we push the x and t axis toward each other, and that's an indication of a non-Euclidean geometry. But that's a standard Minkowski diagram, so it's still well understood. But it helps us to visualize different space-time effects. So with this idea, we can probe space-time. It's a lot like we probe matter. We start pushing it and see how it reacts. So here we would push these spatial hypersurfaces. And we don't even need the full axes. We just have to know where the new spatial hypersurface ends and after this transformation. And we draw little arrows here for the normal direction, which indicates the non-Euclidean right angles. So in special relativity, we have just hyperplanes. It's a well understood procedure, but for us it's important we can easily extend this geometrically to more complicated situations. We can first use curved lines or curved hypersurfaces instead of just hyperplanes. And everything still works. So in the 70s, people derived Einstein's equation from just requiring consistency with these transformations. So that these geometrical pictures are in some way more fundamental than the equations of motion. And what we're trying in quantum gravity is try to replace this picture with something that's discrete, so discrete deformations. And we still don't know how that works or if it can be consistent. But at least in some simplified situations, it can be analyzed. And that's how we noticed this relationship between just four-dimensional space and space-time at high density. So the way this works, first an illustration of the difference between space and space-time on the left-hand side first. That would be a space-time diagram. We just draw these hyperplanes, just lines, straight lines, in this illustration here. And we draw something like a commutator. So in actual calculations, one would compute commutators, but we can also do this geometrically. So blue and red here now indicate two different deformations of the initial spatial hypersurface. So instead of just having one of them here, we just repeat the procedure with the second one. And then we can flip the two. So here it's first blue, then red, and here it's first red, then blue. And because the arrows from this middle hypersurface here point in opposite directions, we get a spatial displacement as the difference between the two outcomes. So the commutator here basically is a spatial shift to the right. If we repeat the procedure in Euclidean geometry, that means we just use standard right angles instead of these modified ones. We get the same kind of commutator, but now the arrows of the second ones point in the opposite direction. So instead of getting a spatial displacement to the right, we get one to the left. So the only difference between space and space-time is the direction, or just a minus sign, actually, which we can sometimes derive from actual commutators. So what we are using to compute these things are also energy functions for gravity or modified versions, and then that allows us, they correspond to time translation generators as usual, and that allows us to compute these spatial shifts. So if we just start with two geometrical models, or general relativity in space-time and a version in just four-dimensional space, we get the difference here. But then what also happening is if we use a modified Hamiltonian that extends our initial modified Friedmann equation to inhomogeneous situation, we see the same transition happening in the same manifold if we just initially start at low density with space-time around us, but then try to evolve maybe collapsing universe to high density. And around the Planck density, we have a transition to the right-hand side. So that's why time disappears and we just have four-dimensional space left. As a continuous transition within one universe, basically, at least one manifold. So we're still trying to understand the interpretation. It's a little bit easier now. After the last few years, it's like a lockdown for the entire universe. Time literally stood still around the Planck density here. But in terms of math, we have to see what that means for actual evolution through the bounds or through the Big Bang. It turns out the same sign factor that we see in these diagrams appears in equations of motion, like gravitational waves or matter waves evolving on these structures. So this beta function here is non-classical, and it's not guaranteed to be positive. So we change the sign. We go from an elliptic differential equation at low density to, from a hyperbolic equation at low density to an elliptic one at high density. And they are they have to be treated with very different initial value problems. So for hyperbolic equations, we can't really just use initial values at one time and then evolve to the past or to the future. With elliptic equations, we need boundary conditions. We have to surround our whole region with boundary values, and that would be a four-dimensional region. So it would include what's normally the time direction for these boundary values. There's some results from mathematics. So if we are close to the transition, where beta goes through 0, we can linearize this function. And that's related to the Tricomi equation, which initially appeared in hydrodynamics with what is the analog of superluminal? Can't think of the right term in acoustics right now. But if we are moving, or if there are waves moving at speeds larger than the speed of sound in these in certain fluids, then it gives rise to similar effects. And the sonic boom is an example. There are certain poles that then appear in the solutions. And all this has been studied since the 1930s in math. So there are some results that we can use and then extend this to a universe model. So it looks about like this. So here, that's supposed to illustrate a bounce model. So we have a collapsing region on the left and then expanding on the right. And then in the middle, we have the Euclidean phase where we have a four-dimensional space, or this beta function would be negative. And using Tricomi's results, to get a well-defined solution, we have to do something like this. So we initially, we can use initial values. So that basically means we choose initial values at the dashed line here, and then we can evolve forward, but only until we reach the Euclidean region. If we want to include this spatial region, we have to modify our initial values. So we can still use initial values on this. So it would be a light ray in this collapsing geometry, so line C here. But we would also have to choose the field values on this curve A here, which is completely in this Euclidean region. And we cannot choose values on the dashed line here. That would be determined by a limiting procedure from the internal solution. So if we have smooth data on the combination of C and A, there's a well-defined unique solution in the interior, which then also gives us values on the missing boundary piece. And then what Tricomi showed for the sonic boom also appears here. So that basically means it's a well-defined solution in the interior, but it generically has a pole-like singularity at the end of this A line. So there's still some divergences, but only at individual points, not all over space as in the original Big Bang model. But it also means if we only get through to the Euclidean phase here, and even to get a solution in this part of the collapsing universe, we still have to assume some future data. So it's not determined only by initial values. And that means it's not the standard deterministic picture. And then once we get everything in the Euclidean phase, we can impose initial values on this dashed line here and then evolve in our expanding universe. But getting through the bounds and the Euclidean region seems to be non-deterministic. So, so that's about the latest result. Again, I have to emphasize we don't have any observational confirmation for pretty much everything I told you. So we don't know if these space-time atoms can even be consistent. We know if they are consistent, then there might at least be indirect effects. They happen on very extreme scales, so we can't probe them directly. But maybe small effects in the cosmic microwave background or gravitational wave background could be derived and then tested. So in terms of observations, gravitational waves are useful because they don't scatter so much at high temperatures and densities. So once LISA starts running, might give us some information, or more precise observations of the cosmic microwave background like CMBS4, which will be a network of telescopes at pretty dry places, so the atmosphere doesn't move too much. And the second network will be right at the South Pole. So we'll just look same direction all the time and give very precise information about the CMB. So to summarize, the singularity is really stubborn. So many people, many different theories have tried to remove it from the standard Big Bang model. But so far it doesn't really seem to work. So first idea was violating positive energy conditions. But then even if we use quantum mechanics, it's mainly a statistical effect that could help us, which does not seem strong enough for the whole universe. And then the more recent alternative is to use repulsive modifications of the gravitational force motivated by discrete spatial structures. And also here it seemed to work initially, but then trying to make everything consistent with a full space-time structure that can also include inhomogeneity, there were new obstacles, and we've learned at least we can't even take time for granted, so the full space-time structure might be extremely modified. So I guess we shouldn't use too many assumptions because most of them will likely be violated. So I'll stop here and take questions if there are any.
Okay, so with the Stoics, the universe is completely deterministic, but at the end, a universe stops by going off in flames and completely collapsing. And at that point, so to say, God, which is still there, kind of, in some sense, you could say, at least in one reading, deliberates and then comes up with exactly the same universe. So it's interesting because you said, well, there's no deterministic connection to the previous predecessor. So there may be some connection to that. But the conceptual question I have is, you talked about cycles and bounces, and it sounded as if you wanted to say only if there's a bounce can it be cycles. And I'm not quite clear, why couldn't we have, so to say, cycles where we have a singularity, we have a universe, and then the kind of universe completely collapses again, and we go back to singularity. Why do we need, on your conception, bounces in order for that to be cycles?
Yeah, so I think you're saying that one could interpret the expansion and following collapse as two cycles. Or a single cycle. Yeah, I think in at least most cosmologists, the way they use cyclic, that the word cyclic is used in this context, it would always mean multiple cycles of this type. So a single cycle would not be considered cyclic for some reason. So if it does that, if it collapses and then there's a singularity at the beginning and at the end, it would be more like a standard Big Bang model. Yeah, right. Okay. Yeah, there are different options. So the other possibility would be to derive a theory of initial conditions, which basically corresponds to what happened before the Big Bang, without actually describing a universe before the Big Bang. So it would give you initial conditions for this one cycle, and so you put together all, okay. Yeah, I think as a space-time model, if you have a singularity, you basically have to remove it. It's a boundary where the math breaks down. So even if you put them together, they would not be completely connected. So a little bit like the indeterministic behavior here, but in this case, it would be completely indeterministic because we would have to just stop once we reach a singularity. And I think there are ways to extend equations beyond singularities, which sometimes works. But also here in general, with all kind of inhomogeneity is mathematically very difficult. And then there are also ideas like Penrose's conformal cyclic cosmology, which does not have a collapsing predecessor universe, but it was expanding, and then he just somehow rescales it at the Big Bang, and that gives rise to a new universe. It would be always expanding, but the expansion rate would not be monotonic. So there are different versions. And I guess all of them are called cyclic. So yeah, I didn't mean to imply that the cyclic model requires a bounds, but in many cases, the first step to constructing a cyclic model is to look whether a bounds is possible, even though it might not be necessary, but that's at least something that can be checked. And I wanted to emphasize here that even a single bounds is usually very hard. And but I think it applies to other scenarios as well. So anything that replaces a singularity has to be embedded in some kind of consistent space-time structure. So the same questions would have to be addressed.
So thank you very much for the talk. So this is similar in some ways to the last question, but I'd be interested in understanding a little bit more what kind of conditions are required for successful bound scenarios. So you might ask like sort of continuity differentiability conditions on the metric. Usually you'd assume that the metric is twice differentiable for Einstein's field equations to be well defined. Obviously that's not going to happen in a lot of these cases. So that's one question. Just how do you think about, when you look at these different proposals, what kind of conditions would be satisfying for a well-defined theory? And then a follow-up is related to the character of the partial differential equation shifting from hyperbolic to elliptic, because is there a positive aspect of that you would get a much stronger set of constraints on the initial conditions, that there's only some sets of solutions for the elliptic equations that would be feasible, and then that might actually allow you to say that there's a much smaller space of possible cosmological scenarios coming out of the bounds?
Yeah, first question, I think in most of these models, people assume differentiability, which may be one reason why it's so hard. So there are other smaller number of studies where people were looking for distributional solutions. Instead of having a complete breakdown at the singularity, it would just not be differentiable, but there would still be a well-defined distribution for the metric or curvature. And in some models, again, that works, but then trying to extend this to full inhomogeneity is tricky. It's basically because in simple models, the singularity is simple. It's just basically collapsing to a point or something like this. In full inhomogeneity with this Belinsky-Kolesnikov-Lifshitz scenario, it's much more complicated. It's more like a fractal at the singularity, and then defining a distribution on that fractal is hard. The second question, what was it? Oh, that's right. Yeah, I don't think it does. Basically, so if you have a second order field equation like we have in GR, then for an initial value problem, you would actually have to impose two functions, the field and its first derivative, and that's replaced by just the field on the combination of C and A. So in some sense, it's the same number of conditions. We just impose the second field, the first derivative, or something analogous to it, on a different curve. So it is not really more restricted unless we bring in additional physics, like something like Euclidean quantum field theory, because it is a Euclidean region. And then there are certain quantum conditions, like a well-defined ground state that might at some point help us. But so far, we haven't found anything.
Okay, an interesting talk. I'd like to mention a theorem that I proved with Alan Guth and Darwin Borde which I think is relevant for cyclic models. So I'm interested in your take on this. So the theorem roughly says that if you have a universe which is on average expanding, it cannot be geodesically complete to the past. So the universe may expand and contract in some periods or some regions of space, but on average, along any geodesic, it is expansion wins. If you keep going to the past, then you cannot keep going to the past indefinitely. You have to stop. This means that cyclic models, which are geodesically complete, are basically impossible. You can have a cyclic model which, because they have to expand on average, otherwise you would have thermal death of the universe.
Yeah. Yeah, thanks for this question. I actually forgot to mention something. So I did say, so there is, it's related to the last point here. So if we claim that we can avoid singularities by bounces, we have to understand how they can avoid singularity theorems like the initial ones or yours that you just mentioned. And so that's something where these Euclidean regions actually help us, because in this case, what we know is, so if we start here on our side and try to extend this backwards, then even if there's no curvature singularity, time-like geodesics cannot be extended to the past because time ends at some point. So we just don't have time-like geodesics anymore. But in this extension, one could argue it might still be geodesically complete, because we could use the final tangent vector and where it reaches the dashed line here, and then use that as initial conditions for a space-like geodesic in the Euclidean region. So formally, that's how we understand how we can avoid the singularity theorems, but it's at the price of losing time and determinism. So in some way, it's still a singularity if you just ask about whether we can extend all possible initial values across this region.
Why is it a problem to lose time?
I don't know. You might have to ask Cervantes, but I think it's a question about determinism. So if you don't care about determinism, you can lose time. And in this, I guess for physics, this would be a little bit like a theory of initial conditions. So we can really constrain what data we can impose on A here. Then we could just mathematically push this all the way to the dashed line here, and it would be a consistent theory of the initial conditions of our universe, like in the first question. The problem is, so far we haven't really found a good way of constraining these values on A. So again, maybe looking more into Euclidean quantum field theory would have to be at very high density. So still not really the Euclidean quantum field theory that we often use in condensed matter physics, for instance. But yeah, it might actually be an opportunity. We just understand it well enough. But for now, we don't.
Thanks for the talk. Maybe it's a small thing, but in some of the diagrams, there was a asymmetry in the two parts of the bound. So I don't know if is there on purpose or if there's for that.
In the plot I showed, in the wave function. Mm-hmm. Yeah. Oh, the widening. Yeah. So this illustrates the whole wave function. So in this case, the expectation value of the volume, so the volume is vertical, and that's time. So the expectation value is symmetric in this model, at least it's a Cauchy function. But there are certain parameters that determine whether the volume fluctuations around this value are symmetric or not. Generically, they don't seem to be symmetric. And it could be a pretty big difference just based on theoretical constraints. But I think even the symmetry in the expectation value is realized only in the simplest models. So in this case, we're really just isotropic and a single matter field. So if we change that, like fermions, which are usually break some reflection symmetries, then even the expectation value might be non-symmetric. And also, I mean, I think that's related to the first point in my questions. If we bring in more and more quantum effects and really treat it like a microscopic system, then there also seem to be solutions that replace the Cauchy with the sinh. So it would really come from down here, goes through zero volume, and then into the expanding branch. So in this case, it would not really be bouncing. Well, I mean, it actually, I should first explain, it would come from negative values, which isn't the volume itself, but volume times orientation. So the volume would still bounce, but it would go through zero. So they are even within the same simple model. So there are still lots of options in the parameters or quantum representations that are not fully explored yet.
Thank you. I just wanted to ask you if you can say something more about the reason why we lose time at the bounds. So particularly, I did not understand if you think we can define cosmic time in relation to the scale factor, even at the phase where there is just four-dimensional space. Thanks.
Yeah, it's really four-dimensional. It's not exactly Euclidean, but so as in this picture, it's there's no time-like direction in this. So there's still a metric align element, but all the directions have positive norms, so they're all space-like. So we could still, we could just decide that maybe something like this should be the normal direction, normal to these hypersurfaces. And mathematically, we could treat it like a time direction, but it would still be a space-like vector. And then if we try to find full solutions for waves, then we would have the problem here of switching from a hyperbolic partial differential equation to an elliptic differential equation. So it's so even if we try to treat this space-like normal as some kind of time direction, it would not be consistent to use just initial values at one value or one transversal section, like one of this dashed line here or something in the middle. It would not be well posed. So solutions might not be unique, or they might not depend continuously on the initial values. So it's really a combination of the metric structure that we derive from this space-time analysis, and then something like the trichomy analysis here to get well-posed initial or initial boundary value problems from the corresponding differential equations. Thank you.